Hello everyone and welcome to the Autodesk Robot Structural Analysis tutorial brought to you by the Civil Engineering Essentials channel. I hope you enjoy the video. In this video, we are going to take a look on the different aspects of modeling and designing retaining walls in Autodesk Robot. To start with, I'm going to select my 3D building design. So retaining walls are structures that, as the name suggests, retain soil from one side that is higher than the other side, which makes them subjected to soil pressure. And this is something that you should have studied in your foundation courses, where you have active and passive soil pressure and Rankine pressure, coefficients and stuff like that. For me, I will let Autodesk Robot deal with that. Of course, retaining walls have two parts, the wall part and the foundation part. And usually they are, in Autodesk Robot, they are designed separately because Robot designs walls alone and designs foundations alone. There is no module in Autodesk Robot that designs the entire retaining wall as one piece. So okay, let's dive into this. So the first thing I'm going to do is I'm going to say that my retaining wall is 3 meters high in the z-axis and also 3 meters wide in the x-axis. Now I know retaining walls are much longer than 3 meters in the x-axis. However, I'm choosing my 3 meters as a sample because usually when you design a retaining wall, you design only 1 meter strips. So I just put 3 meters for good measure. So now I can start applying my stuff. So I'm going to basically do me a floor. However, this floor is now no longer a floor or a slab, it's going to be a wall. So to do that, I'll basically remove the tick from the horizontal slab. And before I continue, I have to define my thickness. Now the thickness of the retaining wall, according to Braja M's foundation book, is 0.1 of H. That's what he suggests to use when you are designing a retaining wall. Of course, there are a lot of recommended values for the retaining wall, so I'm going to show you a quick figure from the Braja M's foundation book. Alright, and I have taken an outtake from Braja M's book, and you can see those are the dimensions that are recommended for retaining walls. Now, since my H, or height of retaining wall, is 3 meters, then the width of the thickness of the wall should be 0.1 H, which should be 30 centimeters or 300 millimeters. There are some slope requirements. If you want, I'll just ignore it and leave the slope requirements as extra, because the thicker something gets, the more safe it becomes, because thicker cross sections mean that the steel is going to be less because the moment arm of steel increases. For me, I'll assume my retaining wall to be of constant thickness of 300 millimeters without any sloping sides. And this coincides with the minimum here and with 0.1 H here, so I'm golden basically. So my thickness here, I just say thickness 300, say 300 millimeters here, apply that or add that. And then of course I remind you to remove the horizontal slab here so that you can start drawing. Okay, so I'm gonna draw that, so I'll just take a look. I'll just go to front like this, and I'll select my rectangle, draw the first line that corresponds to the local X, draw the second line that corresponds to the local Y, and have my slab, or my wall in this case, defined. Of course, those are the local dimensions or directions of my wall. All right, fantastic. Now we need to basically apply some fixation to the bottom of it. Now a retaining wall is fixed at the bottom, and I can assure you that this is the correct way of assuming the support, because when you design retaining walls, you design the foundation to resist overturning, resist sliding, and of course resist the stresses. So there is no rotation, there is no sliding, it should be fixed. Now you can see that I have fixed the entire edge, and to apply a support to an edge, all you have to do is to select the support and go to your slab. Now when you go to your slab, you can see that the slab gets highlighted and one of the edges gets a thick line, whereas the others are just dashed. And this edge gets the thick line when my mouse comes closer to it. You can see that how I'm cycling between edge 2 and edge 4, or edge 1 in this case. If you click now, you apply the fixed support. Alright, fantastic. Retaining walls are usually subjected to geotechnical loads, or basically loads that arise from soil, so you should be able to define that. However, some retaining walls might be also subjected to live loads and dead loads, and the reason behind that is because maybe the retaining wall is part of a structure Technically speaking, a basement wall is similar to some extent to a retaining wall, and the difference between a basement wall and the retaining wall is, well, that it basically connects to a slab that transmits to it dead loads and live loads. So yes, sometimes retaining walls or basement walls in that with that regard are subjected to live loads and dead loads. For me now, I'll just apply me some geotechnical or soil pressure loads without any regard to dead load and live load, because I'm assuming that this only retains soil and that there are no live loads or dead loads around it. So I'll just now open me some cases, consider this to be dead, consider this to be live. And then here comes a little bit technical. Some codes do differentiate between earth and dead loads, whereas some other codes do not. However, the ASI code doesn't differentiate between them. You cannot see anything related to earth loads. Now this E that you see here is for earthquake or seismic, and the reason why there is 1.0 is because the ASI code assumes that you are using the IBC or a compatible code to basically calculate the earthquake loads, and in that compatible code the earthquake loads are already factored. That's the reason why you have 1.0 here. All right, fantastic. So I can assume, according to the ASI code, that my lateral earth pressure is going to be considered similar to dead load. A small hint to the designers among you: ASI code clearly states in its commentary that if your earthquake loads are based on service loads, then a load factor of 1.4 is applied. Anyway, I'm going to deal with my soil pressure as dead load. I will not even consider live load because I'm assuming that there is no live load on my retaining wall. Maybe in the future I would include a basement wall in a structure, and then there would be live load, but for now there is nothing but dead load. All right, fantastic. So let's define our loads. To define geotechnical or soil pressure, you have two options. The first option is to calculate it yourself doing your foundation or geotechnical work, meaning that you have the soil properties, which has the cohesion and the friction angle, and to calculate the soil pressure factors according to Rankine or any other theory, and then calculating the loads, pressures applied, and then applying those pressures. So the actually recommended option of modeling soil pressure, at least from my point of view, is to let robot do it himself by going to loads, special loads, soil pressure, and a window opens that of course asks you which load case are you going to apply the soil pressure. I'm going to apply it to the dead load. I'm applying this to panels, and to which panels am I applying this? So you click on basically the list of objects and select your objects. Now it is selected. Now two questions arise. The first question is basically what are the soil layers are used to generate the pressure, and the second question is, well, how is the force going to look like? The local AZ direction defines where the load is going to be applied, and you can see that you can use it according to the local surface system or opposite to the local surface system. I leave it for opposite as for now. The second question is to define the soil parameters used to apply the pressure. So you click on parameters basically, and now you can see something very similar to what you do in your geotechnical course. Now the soil inclination is basically how much the soil behind the retaining wall is inclined, and in my case I'm assuming that my soil is perfectly horizontal. The inclination actually affects how the soil pressure is applied on the wall. Of course, for more information, I highly recommend a reference, which is Foundation Engineering by Braja M. It's a very nice book. I studied it personally back in my university days. For the wall inclination, my wall is perfectly vertical, so I have no wall inclination. And the nice thing is that if you click on something, you see that the picture highlights this something for you so that you basically understand what is happening. The second thing you see here is there is K node, K active, and K passive. This has to do with the motion expected from the wall. Now, if the wall moves away from the soil, then you have an active pressure. If it moves towards the soil, you have a passive pressure. And if it just doesn't move anywhere, you have at rest. Now, for me, I'll assume it to be an active soil pressure because I'm expecting the wall to be moved away by the soil pressure. So I just leave it as active. Of course, you can take something in between at rest and passive and active. You can choose any point in between them. I'll just go full active. You can apply distance to other objects. This affects the soil calculation. You can even apply an underground water level, which means that you would then have some changes in the density as well as additional water pressure due to the poor water pressure that will be applied to the retaining wall when you have an underground water level that is relevant. For me, I'm assuming that there is nothing there. All right, fantastic. Now I need to start defining my soils. Now there are two options. The first option is that you use the soil templates characterized here. The second one is to use your own soil. So you can basically call, for example, here my own soil, basically here. Say the level of my own soil is at 3 meters because, well, the retaining wall is 3 meters high. For example, the unit weight of my own soil, of course, now is where your geotechnical skills and your geotechnical lab report comes into play. And the difference here being where the unit weight here is the bulk unit weight, where the voids and compaction ratio do have an effect, meaning that if you have higher compaction to the soil, the unit weight increases. If you have lower, the unit weight decreases. The unit weight of solid is basically the unit weight of the stone pebbles themselves. The friction angle is, well, as the name suggests, the friction angle of the soil. Of course, you can choose other soils, for example, clay and stuff like that, and now you have anything you want. You can, I'll just say my own soil basically, and I'll change the friction angle to 23, for example. 23, not 300. And you can choose anything you want here. Of course, you can layer your soil. By layering your soil, I mean you can even apply another soil like this. I'll take it as sand, for example, here, and change the color basically. And you can see now that you have 2 layers of soil. You can actually move them. And you can define anything for the second layer. And you can even define a third layer if you want. And you can layer your soil however you find fitting. For me, I just assume that there is only one type of soil. I even chose my own soil because usually those values are something that you are going to provide from the geotechnical test that you have done in the site. If you don't know, or if in your case you know exactly what kind of soil you have, then you can select whatever you want. Anyway, I just leave it as is. You can save this profile if you want to reuse it again and again. This is especially useful when you have a basement wall and you need to apply the same force over and over again to each one of the basement walls. You can go to loads now and you can apply a surcharge pressure, and you can even select the code that is used to model that. You can apply any pressure, and you know, of course, that pressure gets translated onto the wall according to any method. For example, there is the 2-to-1 method if you want. Now I'll leave it as is. The results give you the forces. You can see here that there is some soil pressure. I click on apply now, and now my soil pressure is ready. If you click on apply again, the soil pressure gets applied, and the value of the soil pressure is calculated from the calculations of robot. Of course, you can calculate it yourself if you want and apply it yourself using hydrostatic pressure if you want. I trust robot on that one and let robot calculate it for me. Fantastic. So now I have applied my forces. Now if you close the window, of course the forces disappear. If you click on load values and load symbols, the loads reappear. Fantastic, I can calculate now. So I run the analysis hoping that nothing is wrong, and I think my analysis is complete. I basically, I don't know, like the meshing is not that nice, it's really big. I mean, if you select the deflection shape, I don't know, I don't like it, it's really awkward. So I'm just gonna improve my modeling here by changing the mesh size. I can do that by going to my job preferences. Of course, I've talked about this previously in the job preferences video linked above. And furthermore, I went into more detail about meshing and selecting the mesh types in yet another video called the basics of panels. You can check that link up on the right side. So I'd select fine, click on OK, run the analysis again, and now actually see something that is much smoother. All right, now the deflection shape makes sense. I'll just go and check out my moments just to make sure everything is fine. So just go to results, maps, and select moments XX. Yeah, I think, all right, fine. Now XX means the horizontal direction, which should not have much moment, but the vertical direction should be a clear cantilever. And you can see, yes, that's a clear cantilever for you. If you still do not see it, well, I suggest that you basically apply a panel cut. So just go to panel cut like this. and apply me a panel cut that is parallel to YZ passing through this point. Apply, and I want the panel cut to show me the MYY, and you can see that this is actually the moment that is used to design the wall. You can actually design the wall, because part of designing the retaining wall is to design the standing wall and the foundation, and you can use this moment diagram to design the standing wall by basically, you can, if you want, assume the wall as a beam that has a width of 1 meter and then design it according to this moment diagram. However, I want Autodesk Robot to design me the retaining wall entirely. So the first step of designing the retaining wall is to design the wall itself, and the second step is to design the foundation. Now you cannot simply go to designing stuff because you still haven't done your combinations. So I don't know, let's double check. I'm just going to do me this combination because it seems it's the combination that gives you the maximum forces, which is 1.4 dead. So okay, I'll just go to my loads, manual combinations. So basically we need to define our ultimate limit state, and as we've just mentioned, I'm gonna apply me a 1.4 dead load because it's only a dead case, so it's gonna apply me a dead load. If I click this, will it accept it? No, it doesn't. Well, so to do that, just click 1.4 here, select my dead load, apply that, so I'm done now. This is according to the ASI code. You might have different codes in your region, so please double check your design codes. Also make sure that your design code deals with lateral pressure as dead load. It depends from code to code. So we've done our calculation, we have our combination, and now I can go to basically geometry like this. Click here, go to reinforced concrete design, and go to slab required reinforcement. So let's double check our calculations. The first thing is my list of panels is 1 because I wanted to run the analysis and the calculation on panel number 1, which is this panel. And the limit state is going to be ULS. However, it's not case number 1 because case number 1 is the dead load case. Let me remind you, if you go back to structure model geometry, you can see that case number 1 is dead load and case number 2 is the combination, meaning when I go back to reinforced concrete slab design, this combination is incorrect, should be 2. So I click on 2 now, and well, I'll just, of course it will verify the deflection and check the displacement of that. I just let him calculate it for me. So now it's calculated. You can see that it actually tells you case 2 combination 1. So now we can start looking at the reinforcement. You can click, for example, on the reinforcement area, what the area steel is, and hit the apply button, and you can see where the area steel in the X direction is required, and in the Y direction, of course, it will be the bottom reinforcement. The bottom means the other side, meaning if you open the local system, the Z-axis determines what top and bottom is. Top is in the direction of the Z-axis, bottom is in the opposite direction. So if you click on Y negative, you might be tricked in thinking that there is no reinforcement in the Y direction, which is counterintuitive. It's counterintuitive because if you go to the geometry, you can clearly see that this thing deflects. I cannot see it, right? You can basically see that this thing deflects to the side, so there must be some reinforcement, which means that if you don't pay attention, you might be tricked into thinking that there is nothing in Y. However, the main reinforcement is in Y, and to show you that, all you have to do is to click Y positive, meaning Y on the positive face, of the wall, and you can see the reinforcement being shown here. And well, I just want to remind you that positive is in this direction, local Z, and negative is in the other direction. Now reinforcement seems to be rather low. Maybe it's because the forces were not that serious, meaning that robot was designing on minimum reinforcement. Might be. I will leave this for you, so try, increasing the loads, increasing the height of the retaining wall. I leave it as is. Now, if you want to take it one step further, of course, there is SLS, and there is, like if you want to have cracking, checking the cracking and stuff like that. If you want to take it one step further, you can actually let Autodesk Robot give you the design drawing for this. Now, how can you do that? Well, you select your wall. And go to the provided reinforcement of reinforced concrete elements, and you will see that it will import for you the wall. It takes some time because robot starts importing, and since the importing is being done, you can see that you have slab 1 here. If you double click on that, you can see that this slab is provided here. All right, now you can of course design it using wire fabrics or using basically reinforcement bars. And how do you do that? Well, you have some options here where you can start looking at the calculation. Now, of course, all those options were explained before in the beam design and column design videos linked above. So I will refer you to those to double check them. I will leave them as is. I'll just not change anything here. I will not be choosing any wire fabrics. I will be relying on reinforcing bars to deal with this. This is the reinforcement patterns where you can choose what you want to use to design. I want to use bars only, and my bars are going to select it automatically. You can play around with this if you want. And well, yeah, that's all what I want to do. Your main bar is going to be a straight line. I run the analysis right now and take a look on what is going to happen. So if you run the analysis now, everything seems to be fine. There are no errors, and the area steel that was provided, it's 560 millimeter at 450 millimeter. That's really not good. I mean, if I go now to my drawing, I really don't like that personally. It opens you this drawing, and you can see that this is like the bottom slab reinforcement, which is 7516. The grade I didn't change, and the top reinforcement, which is this thing, which is, you can see that there's a little bit more reinforcement here in the y direction than in the x axis. I still don't like that. It's really low, and the reason why I don't like that is because, and this is for you a small hint, I don't like that because the spacing between the reinforcing bars is too large, and this will be a problem when you have to control crack, because usually there are maximum distances recommended for the spacing of bars. It's not recommended to have huge concrete distances without any reinforcing bar. So my suggestion to you is to decrease the diameter and let robots run the analysis again to find the adequate design of that wall. I'll just show you how it's very quickly done. I'll go to provided reinforcement, double click my slab, and basically force it now using my options here. I will force it to use phi 10, for example, for the reinforcing bars. And yeah, I'll just force it to use phi 10 and run the analysis again. Now remember, the forces are not that serious, and that's why the reinforcement was very spaced, very far away spaced. If I click now, well, yeah, now it makes more sense because the distances between the bars is less, and this is good for crack controlling. All right, so I think I'm done with this. I will leave it for you to can actually go to drawing parameters and play around with the things that you want to see. And you can also go to the drawing and basically start playing with your drawing. Of course, you can finally, if you go back to the design and go to the provided reinforcement, so let's go to provided reinforcement, to the slab. Of course, you have everything that you want. Here you can have a calculation note, which gives you the calculation node that was used in designing the slab, or the wall in this case. And in the end, you can see the steel density. It's rather low. I mean, I'm assuming, I was expecting something in the hundreds, but remember the forces were low, so the steel weight in comparison to the metric cube of concrete was rather low. Of course, you have your nice reinforcement distribution and length that are required. This is good for shopping and buying, basically, or cutting those reinforcements. Yeah, I think I'm done with the wall. So let's take a look on the foundation. Now, how can I design my foundation? I go to geometry and basically select my fixed support here in the bottom, like this. Design, provided reinforcement for reinforced concrete elements, importing the forces. I will take the dead load and I will let robot do it himself, calculate the combinations himself. Because I've just done one example with my own combination, I will let robot do it himself. So when I took the foundation, if I click now here, you can see that Autodesk Robot defined a long foundation, a wall foundation, which is exactly what I want, basically. And you can see from the foundation view that the wall seems to be in the center, but no problem, the wall will be shifted once robot starts calculating, because robot tries to shift the wall so that the eccentricity eliminates any moments on the soil. Now, I want to stick with Braja M-'s recommendation. Yeah, so Braja recommends that the toe of the slab or toe of the retaining wall is 0.1 H, meaning that it's 30 or 300 millimeters. So I will fix that. Now, how can I fix that? Well, it's according to the eccentricity. The eccentricity measures the distance between the center of the wall to the center of the retaining wall. Now I don't know what the retaining wall's base is, so I'll just first of all design and then I will shift my wall. So let's see what happens. Maybe a robot will automatically do something that is recommended by Braja or not. I will check it out, design, and then check out what will happen. That's the beauty of the design process. You don't know the answer beforehand, and personally, when I do those tutorials, I personally try not to know the answer beforehand. I am purposefully oblivious to what is going to happen to me right now. The reason behind that is because I want you to see my thought process in detail rather than just giving you an example where everything works perfectly. I like to show you the step-by-step suffering that I endure. Okay, now all those options of foundation design were covered in a foundation video that is linked above. For me, I'll just go quickly to my geotechnical properties. And well, this is a retaining wall, meaning that there is soil on one side and no soil on the other. The loads from the soil above the retaining wall are already included, and they are included because I have imported the loads, and you can see that if you cycle the loads, you can see that all those loads were the reactions of the fixed support of the retaining wall. So what I'm trying to say here is that when you go to soil, the soil above the zero level is already included and already taken into account, because the reactions of the support are going to be the actions on the foundation. So no need to model the soils above the zero level. Fantastic. Now, I'm going to say that my retaining wall has the following soil structure, meaning that the height of the soil on one side is different than the height of the soil on the other side. My design of the retaining wall, I'm going to leave it like at 1 meter below the ground. So you can see it's now 1 meter. And on one side, I want it like this. On the other side, I want it to be 50 centimeters less, or maybe 30 centimeters less. So I'll say here negative 0.3. So you have now a differentiation between the soil on one side, the soil on the other side. Now there is a minimum soil cover on the retaining wall if you want to include that. I will just leave it as is. Just wanted to show you that yes, you can actually introduce different backfill heights on each side of the foundation. I think this was 23, I think, if I remember. So I'll just do it as I have done before. I just leave it as is now. Of course, you have to check your geotechnical report and know what kind of soil you are using here when you're designing your foundation. All right, fantastic. So let's close that. Go to my geotechnical options. Of course, there is a safety factor against the rotation of the support, and against average settlement and contact surface and stuff like that. There is also the stress, the allowable stress of 0.3, which is, I mean, respect. It's a good soil actually. I just leave it as is and run the analysis and see what will happen. Now, running the analysis, you can see that Autodesk Robot doesn't respect at all the recommendations of Braja M. It threw the wall on the exact opposite side of the recommendation of Braja M. because it tries to fight the moment that is being applied from the reaction. Let me show you what I mean. If you go to geometry, you see that this totally doesn't align with what you have learned in geotechnical. You can see that you have learned that a retaining wall looks like this, but robot actually takes the wall and puts it here, which doesn't make sense. Now, it does make sense for robot, it doesn't make sense for us. And allow me to elaborate on this sentence. It does make sense for robot to throw the wall to the side because robot tries to minimize the eccentricity on the foundation. So if you go to the provided reinforcement, I will show you what I mean. If you go to foundation results, you can see that robot tries as much as possible to keep the pressure below the retaining wall as equalish as possible. Now, in our case, it doesn't make sense because robot doesn't know that this foundation is a retaining wall foundation. And what ends up happening is that we actually, as geotechnical engineers, rely on this heel in providing us with stability against overturning and stability against sliding, because this soil weight above the heel actually provides a counter moment that withstands the tendency of the retaining wall to overturn. Furthermore, the weight of the soil coupled with the friction angle of the sand provides means of resisting the sliding of the retaining wall. Now, Autodesk Robot doesn't know that. And that is one of the weak points of designing retaining walls without proper engineering input. So to fix that, I will go now back to my reinforced concrete design and now actually fix the eccentricity of my wall by going to foundation view and selecting eccentricity of -1.1. So I'm forcing it to be on the toe side. This is exactly opposite of what Autodesk Robot wants me to do. But I'm forcing it because I want to design a retaining wall and I want to force Robot to design me this retaining wall. So I want it to design the retaining wall, which makes sense now. If you want this to look actually cool, you can right click here, click on display and go to panels and open panel thicknesses, and suddenly you have such a cool retaining wall if you want it to look cool. All right, fantastic. So let's get back to our design now. So I'm going to tweak a little bit with my eccentricity. Say my eccentricity is 1 meter. Hit the apply button, and I will fix that because I don't want Robot to change this value. I'll apply that right now and run my calculation. Maybe it will work. It does. Perfect. If I go to foundation results, you can see that there is a huge pressure on one side and small pressure on the other side. That is the reason why Robot tried to move your wall to the other side, but we have stopped it from doing this because we are designing retaining walls, and this is why we need humans after all. That's why me and you as engineering humans are very important, because softwares don't understand this. We, the human, know the full picture and know that the retaining wall needs its heel so that it is able to withstand the rotation and the sliding of the retaining wall. So yeah, I think, I think everything is fine right now. So if I go back to my reinforced concrete design, to the provided reinforcement, click on the foundation. You can, of course, go to the foundation results, see the results. Of course, you can see that you have the 1.4 dead load, ultimate limit state. You can go to the foundation reinforcement, check out what this is. Of course, I need to modify it and move it a little bit so that I can see stuff. And yeah, you can see everything perfectly fine. And that's how you design retaining walls in Autodesk Robot. Of course, there is more options if you want. You can, for example, change the type of the reinforcement used in reinforcing those bars. For example, for the main bars, you can apply hooks if you want and force the hooks to be applied just to, look a little bit cooler. And you can see that my bars are now hooked. And of course, you can check out the calculation note if you want, and you can send this to the drawings. And this was discussed in a previous video. For example, here you go to calculation note, you can see everything here, and you can go to the drawings and see your retaining wall being drawn in its full glory. And this is amazing for me. I mean, I usually love to work with Autodesk Robot. It's such a nice software, and well, it accelerates my workflow a lot. I'm done with retaining walls. Now, this is only one type of retaining walls. There are other types of retaining walls. For example, backbone retaining walls with abutments and stuff like that. There are retaining walls where the horizontal reinforcement becomes the main reinforcement, especially if you have abutments or like columns that stiffen the retaining wall in the vertical direction. These are other topics I will cover in the future. For now, I hope that you have enjoyed the video. Of course, if you have enjoyed the video, please thumbs up, comment, and subscribe to the channel. Subscribing to the channel helps me a lot in increasing my reach. And well, until I meet you the next time, this is the Civil Engineering Essentials channel, and we will catch you in the next video.